Good morning, students. So in the last class we have seen a universal shift register and uh, uh, and also we have seen the synchronous binary counter, right? So in today's class, and this will be the last class of this module. Okay, so we are going to see shift register based counters, right? So here we are going to discuss two counters. One is ring counter and second one is the Johnson counter, right? So please be careful, concentrate on these two counters because you're going to implement these two counters in the lab. Okay, so here we have already seen what is a shift register, right? So what is a shift register? It is a sequential circuit which shifts the data which is stored in the flip-flops towards either towards right or left. Okay, and these are also used to perform the division and multiplication by 2 in microcontroller or microprocessor and ICs, right? So these are the blocks which are used to perform multiplication by 2 or multiplication by division by 2, right? So if you shift the data towards left, then it is like a multiplication by 2, right? And if you shift the data towards right, then it will be division by 2, right? So we have already seen what is a shift register. Either you take a left shift or right shift register, that doesn't matter, right? For this shift register based counters, we have used D flip-flops to explain the shift registers, right? And what was the circuit? The output of first flip-flop. So here it is a synchronous shift register. Why it is called a synchronous shift register? Because the control inputs of all flip-flops are shorted together and they are connected to a common signal called clock, and the output of one flip-flop is connected to the input of next flip-flop, right? And this is also called as a ripple binary counter, right? And here how can I modify this into a counter, right? So what I'll do here, I'll just connect Q4 to the first input. Q4 is the output of last flip-flop and D1 is input of first flip-flop, right? So here I'll connect Q4 to D1. So because of that, what happens, that we will see now. This is the simplest circuit of shift register based counter, and this is also called as ring counter. Why it is called ring counter, later we will see, right? So now what happens, let us assume the first flip-flop is set. The first flip-flop is set, that means it is storing 1, and other flip-flops are reset, that means the other 3 flip-flops are storing 0, right? So what happens now, if I apply clock pulses to each flip-flop, what happens, Q4 is connected to D1, that means when I apply the first clock pulse, let us say I'll explain it with only 4 to 5 clock pulses, because after that the states are going to repeat, right? So this is a clock pulse, this is a clock which is connected to all the flip-flops, right? So now initially initially Q1 is 1, Q2 is 0, Q3 is 0, and Q4 is also 0. So what is the state which is stored in these flip-flops? It is 1, this is 1, 0, 0, 0, right? So when the first rising edge of the clock occurs, what happens? Q4 is connected to D1. Since Q4 is 0, which is connected to D1, so what happens to first flip-flop? It is a D flip-flop and the output follows the input. That means Q1 will become equal to 0 at first rising edge of the clock, right? And what happens to Q1? What happens to Q2? Since Q1 was 1 initially, right? So that is connected to D2. So Q2 becomes 1, right? So and Q3 and Q4 will remain 0 because Q2 was 0 initially and Q3 was 0 initially, right? So this Q3 is connected to D4, so Q4 will remain 0, and Q2 is connected to D3 and Q3 also remains 0, right? So now this is the first state. That means what I can write, Q1, Q2, Q3. Sorry, I took Q1, Q2, Q3, Q4, right? So initially Q1 was high and rest all are 0. Now after, this is the initial state of the counter, right? So now if I apply the first clock pulse, so what happens? Q1 will become 0 because Q4 is connected to D1, and Q2 will become 1 because Q1 is connected to D2, right? So what happens here? This one gets shifted towards right, right? And this 0 will appear here. This 0 will appear here, right? So now when the next clock pulse is applied, again Q4 is 0, right? Which is connected to D1, so Q1 will become 0, right? Q1 will become 0. Q2, what happens to Q2? Q1 is to D2, Q1 is connected and Q1 is 0, so Q2 becomes 0. So this is 0, this is 1, this is 0, and this is 1. 0. Q2 becomes 0, right? And Q3, since Q2 is connected to D3 and Q2 was high previously, or the previous state of Q2 was high, so which is connected to D3, so Q3 will become 1 and Q4 will become 0. So this is at third clock pulse, sorry, at second or third. This is first clock pulse, second clock pulse. Q1 0, Q2 0, Q3 will become high, and Q4 remains 0. So what we got here, 0 0 1 0, 0 0 1 0, right? So now after application of next clock pulse, Q4 is 0, which is connected to D1, so Q1 will become 0, Q2 will become 0, Q3 will become 0, but Q4 will become high, right? So Q3 remains 0, Q1 remains 0, Q2 remains 0, Q3 will become 0, and Q4 will become high. That means after application of third clock pulse, this is 0 0 and this is 0 and this is 1, right? So now if I apply one more clock pulse, so what happens here? At this rising edge of the clock, Q4 is connected to D1 and Q4 is high here. Q4 is high, so which is connected to D1, so Q1 becomes 1 and Q2 becomes 0, Q3 becomes 0, Q4 becomes 0. That means what we got here, Q1 will become 1, Q2 will remain 0, Q3 will remain 0, and Q4 will become 0, right? So the same states are going to repeat, right? So this was my initial state, right? So this is my initial state. Even if you apply more number of clock pulses, these 4 states are going to repeat. That means if I write a truth table of this counter, so how it looks. First output is Q1, second is Q2, third is Q4, 3, and fourth one is Q4, right? So initial state what we assumed was 1 triple 0, right? So after application of next clock pulse, this one got shifted towards right, and this 0 got shifted towards right, this 0 got shifted towards right, and this 0 will appear at this place, right? So this was the next state. Now when I apply next clock pulse, 0 0, this one got shifted towards right and this 0 will shift towards right, right? Now after application of next clock pulse, this becomes 0 0 0 and 1, right? So again if I apply the next clock pulse, what we will get? We will get the same state as we have started with that state, right? So that means when I connect that circuit, when I connect the circuit which I explained in the previous slide, we will get only the 4 states. I can call these states are states as well as count values. I can call these states as count values, right? So why it is called as a ring counter? Because this acts as a circular shift register as well, right? Because see here, after application of 5th clock pulse, this 1 is not getting destroyed, or it is not going to be shifted. It will be rotated, right? So it will not go out of the circuit, or it will not vanish, right? So this will be retained again by connecting Q4 to D1, right? So this one is retained at this place. That means the last one is again stored back in the first flip-flop, right? So it works in the form of ring, right? Or nothing but a circular shift register, right? So for that reason, this counter is also called as ring counter, right? Or sometimes it is also called as mod 4 ring counter. Why mod 4 ring counter? Because it has total 4 states. This is one state. I can call it as, if I treat this as a LSB and Q4 as MSB, then this state is 1, this state is 2, this state is 4, and this state is 8. So 8, 4, 2, 1. These are the count values what you are going to get if you connect 4 D flip-flops in cascade and connecting the output of last flip-flop to input of first flip-flop, right? So this is mod 4 ring counter. Along with this mod 4 ring counter, we are going to discuss one more counter which we call it as a Johnson counter, or which is also called as mod 8 Johnson counter. Johnson counter, and it is also called as, sometimes it is also called as mod 8 Johnson counter, right? So in case of mod 8 Johnson counter, the circuit is going to remain same as a ring counter. The circuit is going to remain as a ring counter, but only the change here is, instead of connecting Q4 to D1, instead of connecting Q4 to D1, we are going to connect Q4 bar to D1. That's it. And we will analyze the circuit, and which all states we will get, that we will see. Okay. So instead of connecting Q4, this connection remains same. Q1 is connected to D2, Q2 is connected to D3, Q3 is connected to D4. Instead of connecting Q4 to D1, we will connect Q4 bar. We will connect Q4 bar to D1. So here what happens, we will see after application of these clock pulses to each of the flip-flop, what happens to the circuit, which all states we are going to get, that we will see now. Okay. So initially, let us again we will start with the same state, initial state, that is 1 0 0. So how we are going to get this as 1? For flip-flop we have two signals which we call it as asynchronous signals. One is preset, second one is clear, right? So if I make preset is equal to 1, this flip-flop is going to set. If I make clear is equal to 1, if this flip-flop is going to reset. That means preset and clear are used to set the flip-flops or reset the flip-flops, or I can decide the initial state of the flip-flop with these two signals. Okay, right? So by using preset, by making preset is equal to 1, I am going to set the first flip-flop state, right? And clear is equal to 0 in that case. But here in the other 3 flip-flops, they are cleared. The states of each flip-flop is 0. That means clears are going to be connected to 1 and presets are going to be connected to 0, right? So preset of all these flip-flops are connected to 0 and clears are connected to 1, right? So now when I set the state and just analyze the circuit, Q1, Q2, Q3, Q4, what are the states we are going to get? I said it is also called as mod 8. That means I need to get total 8 states including 1,000. So when I start with 1,000, Q4 bar is connected to D1. That means when Q4 is equal to 0, Q4 bar is equal to 1. So this 1 is connected to D1. That means Q1 will become 1, right? Q1 will remain 1 and this 1 gets shifted because of this connection to next flip-flop. Next 0, 0, right? Next Q4 is again 0. Q4 bar will become 1. So Q1 will become 1. Then 1 gets shifted here. This 1 gets shifted towards right. This 0 gets shifted towards right. Right? So total 8 states I need to get with this setup of the circuit. Next again Q4 is 0. Q4 bar is 1, which is connected to D1. So Q1 will become 1. This 1 shifts here, 1 shifts here, this 1 shifts here. So these are the 4 states. Along with this we will get 4 more states. I will write those 4 states here. Okay. Since now Q4 is 1. Q4 is 1. The previous value of Q4 is 1 and Q4 bar will become 0, which is connected to D1. That means Q1 will become 0, right? And this 1 shift towards right, this 1 shift towards right and this 1 shift towards right. So after 1 1 1 1 we got 0 1 1. Next Q4 is again 1. Q4 bar is 0. Q1 will become 0. Q2, this 0 shifts towards right, 1 and this 1 shifts toward right. Next 1, again 0 0 0 1 and finally this is 1, Q4 0. So these are the 8 states what we are going to get, and after this again Q4 bar will become 1, which is connected to D1. So Q1 will become 1. Again we are going to get after this state again we are going to get this state. That means totally we are going to get total 4 states. This is not a state, okay? This is not a state. These are the 4 states plus these are the 4 states. So total 8 states we are going to get, and hence we call it as mod 8 Johnson counter, right? So what are the state values or the count values? You can also write the count values in decimal, right? Q1 is LSB, Q4 is MSB, right? So here this value is 1, this value is 3, this is 7, this is 15, okay, and this is 14, this is 12, this is 8 and this is 0. So these are the count values, random counts you are going to get, right? So in exam they will ask rig up a circuit for ring counter and Johnson counter and explain, right? So in that case you have to draw a circuit, right, and little bit explanation how it is going to work, and this state table or truth table you have to write, right? So this completes your third module, right? So in the next class we are going to see how actually these counters are going to be designed using different flip-flops. So we are going to use all 4 flip-flops what we discussed in this module, that is D flip-flop, T flip-flop, SR and JK flip-flop, and actually you are going to design the digital counter. Okay, thank you.